Assalamu alaikum to one and all. In this episode, we are doing a revisit to the basic concepts of capacitors. What are the factors that affect the capacitance of a given capacitor? How do we compute the electric field between two parallel charged plates in a capacitor? Find out by sticking around, watch, and learn. Question number 1. If a capacitor capital C1 is equal to 4 microfarad and another capacitor C2 equals 8 microfarad are connected in series, which has the greater amount of stored energy, capital U? What if they are connected in parallel? Which has the greater amount of stored energy? So we have some options. Option letter A, if they are in series, it is capacitor number 1. If they are in parallel, it is capacitor number 2. Option letter B, it is capacitor number 2 if they are in series, and capacitor 1 if they are in parallel. And option letter C, the amount of stored energy, capital U, is the same for both series and parallel connections. The figure here shows the arrangements of three capacitors when they are in series and when they are in parallel. So for capacitors connected in parallel, their equivalent capacitance or total capacitance denoted by C sub T. Alright? It is just equal to the sum of the individual capacitances, that is C1 plus C2 plus C3. But if the capacitors are connected in series, then the formula for finding the equivalent capacitance or total capacitance, okay, is expressed in terms of the reciprocal. That is, 1 over C sub t is just equal to the sum of the individual reciprocals of the capacitance or capacitances. That is, 1 over Ct is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Alright? Basically, capacitance is just equal to the amount of charge big Q divided by the amount of voltage or potential difference, capital V. And when the big charge or big Q is expressed in coulomb, while the voltage is in volt, then the corresponding SI unit for capacitance is the farad. And we say that 1 farad is just equal to 1 coulomb per volt. Likewise, we also have the formula for computing the stored electric potential energy, or simply energy. All right, the amount of energy that is stored in the electric field of a capacitor that is denoted by capital U. So when the capacitors are connected in series, all right, we use this formula, all right. The stored energy capital U is equal to the square of the equivalent charge. In other words, the charge big Q in the circuit divided by twice the amount of the capacitance, all right, or the equivalent capacitance. That is if we have two or more capacitors connected in series. And when the capacitors are connected in parallel, the formula for computing the stored energy capital U is 1/2 the product of the capacitance, all right, understood to be the equivalent capacitance, multiplied by the voltage or the square of the voltage, okay, in the circuit, right? But we have a general formula which is applicable uh, for either series or parallel connections of the capacitors. And that is, big U is just equal to 1/2 the product of the charge big Q and the voltage capital V, right? So, in this question, we're asked um, which between the two capacitors, the one with smaller capacitance or the one with the bigger capacitance, will be able to store the greater amount of energy. All right? If, for letter A, if they are connected in series, and for letter B, what if they are connected in parallel? So, our concepts, okay, are summarized in this table. All right? We know that when capacitors are connected in series, uh, the charge Q is constant, all right, regardless of the amount of the capacitances. Big Q is constant, and based on the formula, U equals the square of the charge Q divided by twice the capacitance, right? So, if the charge big Q is constant, then we say that the amount of stored energy big Q is inversely proportional to the amount of the capacitance, right? That is, if the amount of capacitance is small, all right, then we will have a greater value for the stored energy, right? But if the capacitors are connected in parallel, where, as you may all know, the voltage is always constant, regardless of the values of the capacitances. No? So, using the formula for stored energy capital U equals 1/2 the product of capacitance in the square of the voltage, right? If the voltage V is constant, then we say that the amount of stored energy capital U is directly proportional to the amount of the capacitance big C, right? Meaning, the bigger the amount of capacitance, the greater is the amount of energy that is stored, right? So, using this analysis, okay, which among the three options in the question is our best answer? All right? So, after analyzing, we get our final answer, which is, in fact, option letter A. That means Um, if the two capacitors are connected in series, then the one with the smaller amount of capacitance, all right, will be able to store the greater amount of stored energy. Whereas if they are connected in parallel, then the capacitor with the greater amount of capacitance can store greater amount of energy. Question number 2. A parallel plate capacitor has a capacitance big C. If the area of the plates is double and the distance between the plates is half, what is the new capacitance? Choices are letter A, big C over 4, option letter B, big C over 2, option letter C, twice big C, and option letter D, 4 times big C. Alright, for this question, our answer, as a matter of fact, is option letter D. Alright, the new capacitance will become 4 times the value of the initial capacitance. Why is this so? Alright, you'll find out as we continue with our discussion. Alright, so for question number 2, we're talking about a capacitor, alright, or the factors that can affect the amount of capacitance, alright, of a given capacitor. So the equation here uh, states that the capacitance, alright, of a capacitor is equal to a constant called the dielectric constant. This is the Greek letter kappa, multiplied by another constant, epsilon naught, alright, which is also known as the permittivity of free space, and then multiplied by the area of the charged plate, right? So, also in the equation, you have the distance d, referring to the distance of separation of the two charged plates, right? So, this constant kappa, known as the dielectric constant, is actually a measure of the ability of a dielectric material or an insulator to store electric potential energy, right? And this dielectric constant kappa may be expressed as the ratio of epsilon, right, over epsilon naught. Epsilon is the permittivity of the given dielectric material, while epsilon naught is called the permittivity of free space or a vacuum, right? So, since it is a ratio of two what we call values of permittivities, kappa is in fact a dimensionless or unitless constant, right? And the value of kappa for most dielectric materials, okay, kappa is greater than 1. And the minimum value of kappa, of course, is equal to 1.0. That is, if there is no dielectric that is made of a material. In other words, if the charged plates are placed in a vacuum, right? So the dielectric constant is understood to be equal to 1.0 or just 1, all right? When there is no particular type of dielectric material used. In short, if the charged plates are in a vacuum, we just uh, use kappa equals 1.0. All right. Actually, uh, the value of kappa for the material air, all right, is equal to 1.0006. All right. So that is almost the same as the value of kappa in a vacuum. All right. Now, to emphasize, epsilon naught has a value equal to 8.85 times 10 to the negative 12 power. The unit is farad per meter. So this is a universal constant known as the permittivity of free space or vacuum. All right. So just to emphasize once more, capital A in the equation refers to the area of the plate or charged plate. All right. Since there are two plates, one is positive and the other is negative, we only consider the area of either the positive or the negative plates. All right. We do not add the two areas. That is what we mean by capital A in this equation. And of course, small letter d is the separation distance. Okay. Usually, the value of the separation distance is much smaller compared to the dimension of the plate. All right. So, in our question number 2, we are told that um, the capacitance, the area of the plate will be doubled. All right. And at the same time, the separation distance will be halved. All right. So we have here our uh, shortcut way of answering the question, because the question is asking for uh, the new capacitance C2. Okay. What would happen to the capacitance if the area of the plate is doubled or twice the original area, while at the same time the distance between the two charged plates is halved. All right. So what we have here is um, a simple way of analyzing the effect of doubling the area and dividing the distance by half, or by 2, I should say. All right. So what we do is C2 will just be equal to 2 times the original or initial area A sub 1. All right. And that will be divided by, because according to the formula, A, the distance is uh, in the what we call denominator. So if you're going to divide the distance by 2, it's just like saying that we are multiplying the distance by 0.5. Alright? And the effect of that is we have here, alright, 2 divided by 0.5, okay, which is the amount of change in the capacitance, C2. Okay, that means the new capacitance will become 2 over 0.5 times greater than the initial capacitance. Right? So dividing 2 by 0.5 will actually result to 4. Right? In short, our answer is that the new capacitance will become 4 times the value of the original capacitance C1. Alright? So that means uh, we are able to explain why our answer for question number 2 is option letter D. Alright? Option letter D, which says that the new capacitance will be 4 times the initial capacitance, or 4 times C1. We now have question number 3, alright, which is a problem-solving question. The plates of a parallel plate capacitor in vacuum are 4.00 millimeters apart and 1.50 meters squared in area. A 5.00 kilovolt potential difference is applied across the capacitor. Compute letter A, the capacitance, letter B, the charge on each plate, and letter C, the magnitude of the electric field between the plates. Moving on to our computations. For letter A, finding the capacitance, we use the formula uh, C is equal to epsilon naught multiplied by the area A divided by the separation distance D. Since the capacitor is in a vacuum, it's understood that the electric constant kappa is equal to 1, right? So, substituting the given quantities, we have 8.85 times 10 to the negative 12 farad per meter, that is the value of epsilon naught, multiplied by the area, 1.50 meters squared, and their product is divided by the separation distance, 4.00, times 10 to the negative 3 meters. So doing our math, we get the capacitance equal to 3.32 times 10 to the negative 9 farad in 3 significant figures. Right? So for letter B, calculating the charge big Q using the formula, Q equals the product of the capacitance and the potential difference or voltage, that's CV, all right? Or 3.32 times 10 to the negative 9 farad, that's the value of the capacitance we just computed in part A. So multiplied by the potential difference already expressed in volts, 5.00 times 10 to the third volts. So finally, we get the value of the charge big Q equal to positive 16.6 times 10 to the negative 6 coulomb. This is the charge on the positive plate. So therefore, the negative plate will also have the same magnitude of the charge, 16.6 times 10 to the negative 6 coulomb, but with a negative sign. And last but not the least, calculating for the value of the electric field using the formula E equals big Q divided by the product of the electric constant epsilon naught times the area of the charged plate. So, plugging in the quantities, we have 16.6 times 10 to the negative 6 coulomb divided by the product of epsilon naught and the area, or 8.85 times 10 to the negative 12 farad per meter times 1.50 meter squared. So once again, doing our math, we get the value of the electric field equal to 1.25 times 10 to the 6 Newton per coulomb. We can check this value of the electric field using another formula. That is, in terms of the voltage or potential difference V and the separation distance of the two plates. All right? So, substituting, we have 5.00 times 10 to the third volts divided by 4.00 times 10 to the negative 3 meter. Right? So, again, doing our math, we get the magnitude of the electric field equal to 1.25 times 10 to the 6th volt per meter or Newton per coulomb. Alright, so you see, we get the same answer. So, for the electric field, okay, you can use this formula, E equals big Q divided by the product of epsilon naught and the area, capital A, or in terms of the voltage, electric field equals V divided by the separation distance D. So that ends my lecture discussion for this topic. Till the next episode, mabuhay, mashallah. Thank you very much for watching. Please follow me in my FB page and please don't forget to subscribe to my YouTube channel.